Good morning, good afternoon, good evening, depending on the time you are watching this video. Welcome again to my YouTube channel, Odavig Structural Hub. This is a place where you learn, build, and innovate. So continue subscribing and hit the notification bell for more content and updates from Vincent or Odavig Structural Hub. Today, I want to solve problem number 2 under timber design to BS 5268. So the question reads, a timber flat roof has a joist of effective length 2.5 meters spaced at 450 millimeter center to center. Design the joist for bending and check shear, bearing, and deflection given that A. Loading imposed equals to 1.5 kilonewton per meter square. Dead load equals to 1.75 kilonewton per meter square. Then B, we have depth to breadth ratio is equal to 3. Permissible deflection is equal to 0.03 times span. And then the length of bearing is equal to 125 millimeter. Assume medium term loading. And then the strength class is C24. Solution. The first thing to do is to determine the total loading. So let's determine the total loading. Total loading is equal to imposed, which is 1.5, plus dead, which is 1.75. So the SI unit is kilonewton per meter square. So the answer is so the answer is 3.25 kilonewton per meter square. 3.25 kilonewton per meter square. The next thing to do is to reduce this loading into from kilonewton per meter square to kilonewton per meter. So how are we going to do it? So you have been told a joist. A joist is a horizontal member. Its length is 2.5 and it is spaced at 450 millimeter center to center. So if we can sketch the joist here, so we can sketch the joist. So that is the joist. So this is the joist and it is spaced at 450 millimeter center to center. Convert this 450 millimeter center to center into meters. So it will be 0.45 meters. 0.45 meters. 0.45 meters. And the effective length is 2.5 meters. So the effective length is 2.5 meters. So for you to reduce this 3.25 kilonewton per meter square, you will do this total is equal to 3.25 kilonewton per meter square times the distance of spacing, which is 0.45 meter. Here 1, here meter. Then you multiply 3.25 times 0.45. So the answer is 1.2 1.4625 kilonewton per meter. So after doing so, now you can sketch again the timber joist and load it. So the effective length is 2.5 and the loading here is 1.4625 kilonewton per meter. After doing so, we will calculate the maximum moment. So moment M max equals to WL squared over 8. So this one will be 1.4625 times 2.5 square over 8. So the answer is 1.14. 1 kilonewton meter. After that, we will also determine the reaction or shear force, which is V. So V is equal to WL over 2. Because this is a UDL, you change it first to a point load and then you divide by 2. So that is 1.4625 times L 2.5 over 2. So the answer is 1.831 kilonewton. After that, we proceed to modification factors. So for modification factor, we will have K3, K7, and K8, as you can see on the board. So we will begin by K3. K3, we have been told, assume a medium term loading. So we will go to the table and see the value for K3, which correspond to medium term loading. So I will show you in the table. As you can see, the medium term, we have 1.25. You can see where my cursor is. So that is medium term is equal to 1.25. So the value is 1.25. K7. So we don't know the depth. So K7, we ignore it. Or we put a question mark like that. We go to K8. K8 will be 1.1. Why 1.1? Because the spacing, which is 450 millimeter, is below 610. If the spacing is below 610, it means we have the load sharing factor. So for any joist that is placed below 610 millimeter center to center, our K8 is always 1.1. So we proceed. We proceed to grade stresses. And let me create space here for more calculation. So the grade stresses. These grade stresses will be obtained from table which correspond to strength class C24. So we will have bending parallel to grain. So this one, you'll get the value from the table. The second one, compression. Perpendicular to grain. Again, you'll get the value from the table. And then we will have shear parallel to grain. Also, you'll obtain the value from the table. I will show you how to obtain these values from the table. So that is the table. As you can see, our strength class is C24. So C24 is here. You can see the movement of my cursor. So we will go straight to the second column for bending parallel to grain. So you can see where my cursor is. So that is 7.5. So we will write here 7.5. 7.5 Newton per millimeter square. We will proceed to compression perpendicular to grain. So you will come again here and the same strength class C24, you'll proceed. You can see the movement of that hand. So we have compression perpendicular to grain. So we have two values, 2.4 and 1.9. So we'll pick the lower value, which is 1.9. So compression perpendicular to grain, 1.9, where my hand is, or where you can see the hand on your screen. So that is 1.9. So we will write that value here, 1.9 Newton per millimeter square. We will go to shear parallel to grain. Again, the same class, which is 2.24. You can see the movement of that hand on your screen. We go to shear parallel to grain. So you can see where that hand is. That is 0.71. So there, 0.71. You write it here again, 0.71 Newton per millimeter square. The final one is E mean. This one will be used for calculating the deflection value. So E mean, you'll again come here and select your E mean. So your E mean is 10,800. As you can see where that hand is, 10,800. So 10,800 Newton per millimeter square, like that. So again, why are we using E mean for this case? Because for load sharing joist, we always use E mean when the spacing is below 610 millimeter center to center. As you can see, the spacing of our case is 450 millimeter, so it means it's below 610 millimeter center to center. So we will use E mean. But if the spacing is above 610 millimeter center to center, we will use E minimum. So now we go to permissible stresses. So let me create space here for more calculation. So permissible stresses. Permissible stresses. So we will begin by bending parallel to grain. So this one will be K3 times K8 times bending parallel to grain, ignoring K7 because you don't know the value for K7. So this one will be K3 was 1.25 times K8 1.1 times stress parallel to grain is this one 7.5. So the answer is 10.31 Newton per millimeter square. So that is permissible stress in bending parallel to grain. Compression perpendicular to grain. So this one will be K3 times K8 times stress perpendicular to grain. So it will be K3 is 1.25 times K8 1.1 times 1.9 stress compression perpendicular to grain 1.9. So the answer is, punch your calculator, 2.61 Newton per millimeter square. And then we will proceed to shear parallel to grain. So this one will be K3 times K8 times stress parallel to grain. So 1.25 times 1.1 times this one 0.71. 0.71. So the answer is 0.98. 0.98 Newton per millimeter square, like that. Now we proceed to design consideration. So bending, we design for bending. So bending. So for bending, we know that F is equal to M over Z. So F is equal to M over Z. So we make Z the subject of the formula. So which imply Z equals to M over F, because Z will give us the section size. So again, we have been given here, we have been told here that the depth to breadth ratio is 3. So depth to breadth ratio is equal to 3, like that. So if we can make D the subject of the formula, so we will cross multiply. Therefore, D equals to 3D, because we are trying to make D the subject of the formula, because we are interested in D. D is the figure that will help us get the modification factor K7. Again, you know that Z is equal to BB cubed over 6, like that. So which implies Z is equal to B, replace this D by this value. So Z is equal to B 3B square over 6, like that. Open the bracket. If you open the bracket, you'll have Z is equal to 3 square is 9. B square is B square times B is B cubed. So we'll have 9 B cubed over 6. So it means if we can have the value of Z, then we can find our B. So let me create space here for more calculation. But you can say but Z again is equal to M over F, and M, we know our M is or our M was so our M is 1.14 kilonewton meter. Convert it to Newton millimeter, so it will be 1.14 times so this one is 11.4 Newton millimeter. Our F is this one, bending parallel to grain, 10.3 Newton per millimeter square. So now you can find Z. So Z is equal to, so Z is equal to M, this value 11.4 over this 10.3. So let me see the final answer. So the final answer is 110.679 times 10 raised power 3 millimeter cube. So this is our Z. Like that. Now, since we have the value of Z, so we can take this value and put it in this equation so that we can find the value of B. So let me create space for more calculation. So I will preserve this one for references. So let me erase this one. So we have Z as 110.679 times 10 raised to power 3 is equal to 9b cubed over 6, like that. So now you can find the value of B. So cross multiply, we will have 9b cubed is equal to 110.679 times 10 raised power 3 times 6. Since we want to get the value of B, divide both sides by 9. So here, 1. So B is equal to the cube root. of 110.679 times 10 raised power 6, raised power 3 times 6 over 9. So if you punch it in your calculator, you will get the value of B. So the value of B is 41 point. Let me create again space here. So the value of B is 42 millimeter. So if you can round it to a whole number, you will find it to be 42 millimeter. So we have calculated the value of B, and remember we are dealing with timber. In timber, it may be difficult for you to find this size of a timber. So we will use a size which can be found in the market, like a size in a multiple of 25, 50, 75, 100, 125. So for this case, we will use a size which is above this one, and the size is in a multiple of 25, 25, 25. So the size is 50 millimeter. So say B equals to 50 millimeter. So we have B as 50 millimeter, and we were told the ratio of depth to breadth is 3. So and we saw that D is equal to 3B. So which imply D is equal to 3 times 50. So this one is 150 millimeter. So the size of timber that will be used to design this timber flat roof is 50 by 150 millimeter. This is the breadth, this is the depth. So now we can calculate the value of K7. We can calculate our K7 because we have our D. So K7 is equal to 300 over H raised power 0.11. So K7, 300 over H raised power 0.11. Because our depth is above 75 millimeters and below 300 mm. So the formula for K7 is this one. So K7 go to 300 over 150 raised power 0.11. So our K7 is 1.10. 1.10. 1.10. So that is our K7. Now you can calculate for Z required. So Z required, let's do it here. So Z required is equal to M over F times K7. So our M was or is 1.14 times 10 raised to the power 6 over F. F is this one, 10.31, K7, 1 point times 1.10. So Z required is equal to 100.52. 100.52 times 10 raised to the power 3 millimeter cubed. So if you can compare this dead with the previous dead, you realize that Z required is less than Z provided. Therefore, okay. So Z required is less than Z provided. Therefore, section okay in bending. After that, we go for shear. We check for shear. Let me create space for more calculation. Now we check for shear. So now we can check for shear. So shear stress is equal to 1.5 V over DD. So this is equal to 1.5 times V. Our V was our reaction, which was 1.83 kilonewton. You convert it to Newton times 10 raised to the power 3 over B 50 times 150. So the answer is, so the answer is 0.366. 0.366 Newton per millimeter square. .366. So you compare this shear stress to permissible shear stress. So as you can see, this one is lower than this. So section of K in shear. So 0. Therefore 0.366 Newton per millimeter square is less than 0.98 Newton per millimeter square. So section K. Like that. Then we proceed to bearing. We proceed to bearing. Bearing. So let me rub this. So bearing. You know bearing, Q bearing is equal to V over Bx. So V is the reaction over the shear force. So V is equal to 1.83 1.83 times 10 raised power 3. You convert it from kilonewton to newton. Then our B is or was 50. And then the X is the bearing distance. So if you can check here, length of bearing is 125, so times 125. So that one is equal to, so 0.29. So the answer is 0.29 Newton per millimeter square. As you can see, this bearing you compare, if you can compare it with the permissible bearing, this one is lower than this. So it means section is okay. So 0.29 Newton per millimeter square is less than 2.61 Newton per millimeter square. Therefore, okay in bearing. Then we come to the final one, which is deflection. So deflection, let me create space here for deflection. So deflection permissible deflection equals to 0.03 times span. So this one is equal to 0.003. The span is 2.5 meters. So 2.5 times 1,000. We are changing it from meter to millimeter. So the answer is 7.5 millimeter. 7.5 millimeter. So induced deflection is equal to induced deflection. So the induced deflection, this is the formula for induced deflection. So we have 5WL raised power 4 over 384 EI plus 24WL square over 5 AE. So if we can break this down, we will have this one. W is the loading on the beam, which is 1.47 kilonewton per meter. So we will have to convert this kilonewton per meter to Newton per millimeter. We know that 1 kilonewton is equal to 1,000 Newton and 1 meter is equal to 1,000 millimeter. So if you carry out the conversion correctly, you will remain with the same figure. Again, we will calculate the area. The area is length times width, so that is 50 times 150. So you get 7.5 times 10 raised power 3 millimeter square. You can obtain this one from the table, from the section table. Yeah, you can obtain this value from the table. Again, we come to length. Length is this one, 2.5. So 2.5, you convert it to millimeter. You'll multiply by 1,000, so you'll get 2,500 millimeter. And then you have the E. E is 10,800 Newton per millimeter square. Again, this one, you get it from the table. I is BD cubed over 12. You can calculate it or you can get it from the table. So if you calculate it, it will be 50 times 150 cubed over 12. So this is the answer. So the deflection is equal to, we can now insert these values into the formula. So we will have 5 times 1.46 times 2, 2,500 days power 4 over this, plus 24 times 1.46 times 2,500 square over this. So you will get 4.89 times plus 0.54. So the final answer is 5.43 millimeter. So you will compare this induced deflection to permissible deflection. So if induced deflection is less than permissible deflection, the section is okay. But if the induced deflection is more than the permissible deflection, then it means the section is not okay in the deflection. So you will again redo the designing and come up with a section that will not result into deflection. So our case, 5.43 is less than 7.5 millimeter. Therefore, section okay in deflection. And our question ends there.